Morning, everyone, and welcome to today's webinar, NGINX HTTP2 Server Push and gRPC. I would like to introduce today's presenter, Owen Garrett, who is Head of Product at NGINX, and he will take you through today's webinar. To ask any questions, please submit them via the question box, and Owen will answer them at the end of the presentation. Please note, a recorded version of this webinar will be available after the event. I would now like to hand you over to our host.
Thank you, Stephen, and hello everyone. Welcome to today's webinar on HTTP2 Server Push and gRPC. My name's Owen, and I will talk you through some of the new features in NGINX that we released over the last couple of weeks, which have rolled into our 1.13.9 and 13.10 releases, and will appear in the next NGINX Plus release as well. So today we'll start with a short introduction, a little bit of a background on NGINX, and I'll then spend a little bit of time talking through how NGINX supports HTTP2. We'll then dive into Server Push and gRPC specifically. We'll have a quick demo of these two capabilities, and then we'll close with a summary and a chance for questions and answers. Let me begin by giving you a little bit of a background on NGINX first of all. NGINX was developed as a front end, a reverse proxy for websites and web applications. Initially to accelerate a portal site called Rambler, developed by NGINX founder, Igor Sysoyev, but now used by millions and millions of websites worldwide. NGINX is fundamentally an open source project with an enormous deployment footprint. We now have almost 500 million websites worldwide, which are published through NGINX. A collection of some of the world's busiest websites, well over 50% of the 10,000 busiest websites in the world use NGINX, through to a total of 447 million domains, hosted using servers with an NGINX header. And these figures come from independent surveys from organizations such as W3Techs and Netcraft, who spider the web and try and determine the technology that sits behind different websites and domains. NGINX, the open source project, is managed by NGINX Inc., founded 7 years ago by Igor and his colleagues, and funded through VC funding and through our commercial activities. We develop a commercial build of NGINX called NGINX Plus, which we provide to our customers on a subscription basis. Those customers receive the full functionality in NGINX open source, some additional load balancing, monitoring, and API capabilities, and of course, full, confidential, accurate support from our engineering team, the team behind NGINX Open Source and NGINX Plus. We have offices worldwide, over 1,000 commercial customers, and grown recently to over 200 employees, with a goal of maintaining, sustaining the NGINX Open Source project and supporting our commercial users. As I described at the beginning, NGINX is typically deployed as a reverse proxy in front of web infrastructure. NGINX can also be used as the origin server, as the web server hosting static content and providing gateway functionality to application code, PHP or Ruby or Java or Go code, and in many cases translating between protocols. For example, when you run a PHP application on a stack such as PHP FPM, you would often deploy NGINX in front. NGINX would receive HTTP, HTTPS or H2 connections and make a new connection to the PHP FPM stack using a protocol such as FastCGI. Other application stacks may use other protocols, So Python, for example, uses uWSGI. Many other stacks will use native HTTP. In each case, NGINX operates as the reverse proxy in front of those stacks, as, if you like, a shock absorber, absorbing large spikes of traffic, filtering out malicious, badly formed, or upgrading old traffic from old clients, and thus protecting the back-end application from the vagaries of internet traffic. NGINX is famed for its ability to scale and handle very, very large volumes of traffic, and then deliver that quickly and accurately to the upstream servers, thus protecting them from spikes and swamps. What I'd like to do now is to delve in a little bit more detail into HTTP2 and give you a basic background as to what HTTP2 is and how it relates to HTTP1, the standard protocol for web traffic on the internet. First of all, it's worth pointing out that HTTP2 is not a replacement or even an upgrade for HTTP1. If you think of the OSI network stack, defining protocols built on top of protocols, HTTP2 is essentially a transport protocol for HTTP1. Websites, web applications still communicate using HTTP1 methods, but HTTP2 provides a more efficient way of packaging and transmitting those requests and responses. Why was HTTP2 developed? Well, in certain circumstances, there were issues with the necessary implementation of HTTP1. HTTP1 was developed over 20 years ago, when the web did not pose the same challenges of performance and scalability and latency that it does now. It was a simple plain text protocol. The client would request a resource through a TCP connection, and the server would send the response. If the client needed multiple resources from the same server, it would make multiple requests, either issuing them in series, one after the other, down the same TCP connection, or opening multiple TCP connections to the same server so that multiple requests could be issued in parallel and satisfied together. Most clients will now open between 4 and 6 individual TCP connections to an HTTP1 server. And the same approach holds if you're using HTTPS, the encryption layer that wraps HTTP. The challenges behind this relate to the load on the server and the speed delivery of content back to the clients. And HTTP2 was developed as an alternative way of packaging HTTP requests to overcome some of those challenges. HTTP2 multiplexes multiple requests and responses down a single TCP connection. A client opens a TCP connection to a server, it issues a request for a resource, and then it can reuse that connection and send more requests while the first one is still in flight. And the server can push multiple responses back to the client down the same TCP connection by packaging those responses up in small chunks known as frames and sending them individually. HTTP2 also brings some other benefits. It uses binary compressed encoding for the header data, which makes a small reduction in the bandwidth required. And although HTTP2 does not mandate the use of SSL, all of the major web browser implementations only support HTTP2 over SSL. So in effect, HTTP2 enforces the use of SSL, of HTTPS, which in most cases results in improvement in security for traffic across the internet. NGINX operates as a terminating proxy for HTTP2 HTTPS, and HTTP traffic. Clients can connect to NGINX using any of the variants of these protocols and issue HTTP requests. And then NGINX's job is to inspect those requests, decide how those requests should be satisfied, typically by forwarding them to an upstream server. And then, in those cases, NGINX makes a connection to the upstream server or reuses an existing keep alive and forwards those requests to the server. Although NGINX supports HTTP 2 for connections from clients to NGINX, currently we don't support plain HTTP 2 for connections to the upstream servers. So we can make either plain text HTTP connections to upstream servers, or we can wrap those in SSL using HTTPS. This way, NGINX operates as a very effective delivery platform, taking a web application that's running on a simple protocol like HTTP, and then making that application available to clients through encrypted protocols and through accelerated protocols like HTTP2. Just as NGINX operates as a gateway doing translation between IPv6 and IPv4, for example. HTTP2 support requires a modern operating system providing OpenSSL 102 or later, because it relies on ALPN as a way of upgrading connections. ALPN is a method by which a client can signal to a server that it is able to support a more sophisticated or upgradable connection than it's initially used. And this support requires OpenSSL 102 in order to function correctly. Our HTTP2 support is now mature. It was released 2.5 years ago, September 2015, in our 1.9.5 release. And it's now used by almost 80% of HTTP2 enabled websites. The chart on this slide is taken from W3Techs, who, as I mentioned previously, are one of the survey companies that scour the internet determining what technology is used behind various websites or various delivery methods. And in this case, as they surveyed all websites that were available through HTTP2, they determined that about 78% of those were expressing an NGINX server header. HTTP2, although a complex implementation, is fortunately very easy to configure and enable with NGINX. Start with an existing SSL virtual server configured to listen on typically port 443 with SSL and a certificate key pair, and simply add the HTTP2 keyword to the listen directive. This will turn on support for HTTP2, which is selectively enabled if a client indicates it can support H2 with an ALPN upgrade message in its connection. NGINX can support HTTP2 over plain text, over clear text, but it does not support any of the standard upgrade methods. So clients need to have prior knowledge as to whether or not they can use HTTP2 when they talk to a plain text connection. In practice, this is very rarely used. Browsers do not support HTTP2 over plain text. But as we'll see when we look at our gRPC examples later on, a simple gRPC application runs very effectively over plain text HTTP, and you can use NGINX as a gateway to publish a plain text gRPC application using SSL to add security if you wish. So next, let's take a look at the first new feature that NGINX supports with HTTP2. Let's take a look at server push. The concept behind server push, the rationale, is that when a client is seeking to render a web page or host or run a web application, there are multiple dependent resources that it requires in order to render the page or run the application. And the server may have prior knowledge that the client does not already have those resources available. For example, it could be the first time that the client comes to that page, or it could be that those resources are not cacheable and have to be delivered every time the client requests a particular page. And with server push, the server preemptively sends those additional dependent resources to the client. The client asks for a page such as demo.html, and the server says, here you go. And by the way, I am pretty confident that you're also going to need the following resources, so I'm going to push them to you over HTTP2. In this case, the server is pushing a style sheet and an image to the client. The client will typically silently ignore that push. It will take the content and push it into a local push cache, but then as it parses the web page and determines that other methods of getting dependent resources. On the left-hand side, the sequential gets, this is the typical pattern for HTTP or HTTPS traffic. A client requests a resource, such as demo.html. It receives the resource, it parses it, and it identifies that there is a style sheet referenced by that resource. It then makes a second request to get the style sheet, receives the style sheet, parses that, identifies that within the style sheet there are some more resources it requires, for example, a couple of images. It then starts issuing requests for those images. Those requests may be parallelized, but as you can see, the dependency graph is a tree-like structure, and as the client moves deeper and deeper into the tree, it can discover more and more resources that it requires and then start issuing requests to retrieve those resources. An approach called preload hints, which uses link headers, has been developed and standardized, and those preload hints can be sent by the server with the initial resource to say, by the way, you may wish to also retrieve these resources as well. That gives the client advance notification that certain resources may be necessary, and the client can choose to check its cache to see if it has those resources cached, and if not, it can choose to preemptively start requesting those resources. So in the case of the preload hints, the second column in this diagram, when the client receives the response for its initial get, it also receives a set of link headers hinting that it may want to preload style.css, image1 and image2. It can then initiate requests for those resources before it's parsed the style sheet or even the original demo.html page and knows for certain that it requires those resources. HTTP2 functions in a similar fashion, but rather than sending preload hints to the client saying you may want these resources, it just goes ahead and starts sending those resources to the client immediately. The goal of server push is to reduce the latency and improve the efficiency by which a client requests resources. And as we released this capability in NGINX a few weeks ago, we ran some tests with a very, very simple page. But, in fact, this demo.html page that referenced a style sheet, which then referenced two dependent small images. And we tried to determine what was the effect of server push in page load times. The key goal of server push is to reduce the amount of time required to load a page, and the key metric that you use when measuring page load time is the round trip time. How long does it take a packet to go from the client to the server and back again? And so this chart describes in detail the effect on round trip time of server push. You'll see that preload has the effect of taking one round trip time out, typically. That's because it sends the hints for the index for the images before the server has had to go and retrieve the style sheet, typically a round trip time. HTTPS adds an overhead in these tests of one round trip time because of the additional handshake to set up the HTTPS connection. But in practice, HTTP2 with server push is comparable to the best case HTTP performance, which is informed by preload. So bringing these things together, you can bring the performance of SSL encrypted content close to or even exceeding the performance of plain text content. How does NGINX, the reverse proxy, know what resources to push to the client? There are several approaches you can take. The first is that you can use the HTTP2 push key directive in the NGINX configuration. Typically that's placed inside a location block, and you can use that to tell NGINX explicitly that it should create a sub request for the named resources, pull those from the origin server or from the local cache, and then push those to the client server. So when you place this HTTP2 push directive within a location block, anytime that location block is matched, in this case, if the request is for a literal /demo.html, at that point, NGINX will then initiate a push for the additional resources. There is no intelligence behind this push. NGINX will push those resources whether the client needs them or not. The client has the option of refusing that push. NGINX sends a push promise. The client can cancel that push. But in practice, for small resources, which can be transmitted within 1 or 2 network packets, then by the time the client sees the stream has started, NGINX will have finished pushing the stream. So canceling the stream will have no effect. This basic method is a good way to push resources that you know for certain the client will need every time it accesses that location or that resource. NGINX also can operate as a proxy, intercepting the preload hints that the upstream application sends and turning those into push messages. An application would tell a client that of the existence of a preload hint by using a link header, as the example on this slide. A link with the URL, the type, and the tag rel equals preload. If you turn preload on NGINX, so you use the HTTP2 push preload on directive, then NGINX will monitor responses from the upstream server, and if it sees link headers that identify resources with the tag rel equals preload, then NGINX will automatically turn those into HTTP2 pushes. It will also send the link header to the upstream to the client. You can also use NGINX to initiate those by putting an add header directive directly in the configuration. That's an alternative to putting the HTTP2 push directive in the configuration. And as we'll see in a moment, it allows you to do more sophisticated, more selective pushes. Here's an example of one of these more sophisticated selective pushes. In this configuration, when a client requests /demo.html, the 3 directives at the top apply. The first directive gives the client a cookie name equals session, value equals 1. The first time the client comes to request that resource, it won't have a cookie, but a client will present that cookie on subsequent attempts to get that resource. We also generate a link header, and we use a map to create that link header conditionally. With the map, if the cookie does not exist, then the link header identifies the resources that the client should preload. If the cookie does exist, then the link header is empty. And finally, our push preload on intercepts that link header and starts pushing resources. If the link header is empty, the client has the session cookie, then we don't push anything. The assumption then is that the client has already retrieved the dependent resources because it's retrieved the primary resource previously. However, if the cookie is empty, if it's not present, then the link header identifies the dependent resources and we actively push those dependent resources to the client. You can monitor the effect of HTTP push using the developer tools in your favorite browser. In this case here, we're using Chrome, and you can see when we get demo.html, it has a number of dependent resources, and those are actively pushed, as indicated by the initiator column. This is a great debugging tool. You can also check out the blog post about server push, and it describes how to test this from the command line as well, using the NGHTTP client. So server push brings some performance benefits and was one of the features which was on our roadmap to deliver as part of our HTTP2 support. The second feature is support for gRPC. So what you may ask is gRPC. gRPC is a modern RPC protocol that's used by clients and servers that wish to communicate in an RPC-like fashion. In an RPC-like fashion, a remote procedure call, a server can implement a function and a client can call that function, and from the perspective of the code, it's more or less transparent whether that function is invoked on the client itself or remotely on the server. The goal of remote procedure calls is to provide a level of abstraction to conceal from the client that that procedure call in fact is running remotely. gRPC by design uses HTTP2. It doesn't work with HTTP1. And the primary reason for that, well, there are two reasons for it. One is the potential efficiency of using HTTP2. The second is that HTTP2 and server trailers together allow the server to generate a response and then return the status code at the end of generating the response. That allows for a more efficient server implementation. Without support for trailers, the server would need to generate the entire response, verify the operation had succeeded, then write the status code, then write the response. With support for trailers, the server can begin generating the response, streaming that to the client, and if at any point during that generation it encounters an error, it can then send a status code to say, what you've received so far is invalid, and send back an error message to the client. gRPC uses HTTP2, and gRPC clients and servers can operate in plain text or in SSL encrypted mode. gRPC calls, as we'll see, are simple HTTP requests. They use post methods. The data in the service call is encoded using a protobuf, and the response likewise comes back as a protobuf. That allows for efficient, compact, and upgradable protocols between the server and the client. NGINX can operate as a proxy between a gRPC server and a remote client. This way, NGINX provides the standard benefits, the protection, the shock absorber effects, so that the gRPC server does not need to have a public IP address, but rather is concealed behind and protected by NGINX. In the simplest case, you can run gRPC over plain text HTTP. You configure a server listening on a plain text port, so no SSL parameter. You enable HTTP2, and you pass traffic to the gRPC server using the new gRPC pass directive. The gRPC :/ prefix is optional. You can leave that out. We've included it in this code example because, as you'll see shortly, you use a different prefix if you want to pass traffic to a gRPC server over HTTPS. And so configuration is very, very similar to the standard methods of proxying traffic with NGINX. NGINX can terminate an SSL connection from a client and then convert that to plain text traffic behind. This means that the gRPC server can run in plain text mode without a certificate. That makes it easier to deploy and manage, and it means that you don't need to pass certificates to your backend application. NGINX then takes that plain text service and publishes it in an encrypted fashion with a certificate on NGINX, so that when clients communicate, they use secure encrypted protocols. The only modification is that the listen server on NGINX needs to be set up to run on SSL mode, and you need then to configure it, obviously, with a certificate and key. You need to make a change to the client application to upgrade it from plain text to SSL, and this is described clearly on the blog that we've published on gRPC traffic. And finally, if you wish, you can also run the upstream server, so gRPC server, on SSL as well. You may want to do that if you're running your infrastructure on a public cloud or in some other environment where you do not fully trust the network. You want to avoid the potential that a man in the middle could be present within your application's network, intercepting traffic between NGINX and the upstream server. In this case, NGINX supports the standard authentication methods for SSL traffic, and you need to make a small code change to your application, your gRPC application, to enable it to listen on HTTPS traffic. As well as proxying gRPC traffic, NGINX is able to do a couple of additional things as well. The first thing that you can do with NGINX is route gRPC requests in different directions based on the request parameters. So for example, in this illustration here, we have a gRPC client that is making several different requests through a common endpoint, a public point hosted and provided by NGINX. In this case, the clients are asking for /service A and /service B. Behind the scenes, your application might implement those gRPC methods in different ways, on different stacks, in different bodies of code. Here, you can use NGINX to route the traffic based on the URL, so that requests for service A get routed to one server, and requests for service B get routed to another server. Furthermore, you can extend that additionally to implement load balancing. Multiple servers can publish the same service, and NGINX will perform load balancing across those servers. NGINX open source provides a range of different load balancing methods, round robin, least connections, and various hashing methods. And it performs basic health checks on the upstream servers. If they fail to accept gRPC connections, then NGINX will conclude that those servers are down, and it will try other servers in your upstream group. And in the demo, we'll see how you can combine these two methods together. The request routing, different servers provide different services, and load balancing. Each service is provided by a cluster of servers to build a scalable and easy to manage cluster of applications that publish services using gRPC. So let's move forwards to the demo. And I'd just like to reiterate, if you have any questions as we go through this session, please drop them into the Q&A box, and I'll endeavour to answer those at the end of this session. So We shall move to the demo. And what I'd like to do first of all is give you a very quick demo of the effect of HTTP2 server push. I have an example here of a map made up of 48 images, tiled. And this is presented over HTTP. The map is hosted on a server where the round trip time is about 150 milliseconds away. On the left, you can see the map. On the right, you can see the waterfall chart as we grab it. And if I shift reload this, now you may not see over the WebEx because it may not respond quickly enough for you to see the effect of the loading. But what you'll see if we dive into the waterfall chart and we look first of all at the load time at the very bottom, we're looking at almost 2.5 seconds, 2.46 seconds to load the core page and then the 48 dependent resources. And this is being delivered over HTTP. As I mentioned previously, clients will make multiple TCP connections to a server in order to retrieve resources in series. They parallelize those requests across those TCP connections. And typically, a client will make up to 6 TCP connections. So when you look at these waterfall charts with HTTP traffic, you often see groups of 5 or 6 connections where requests start, they're queued and delivered, and then in this example here, because of the internal scheduling of those requests and slight jitter between how quickly they responded, they begin to diverge. But you can see that requests are being issued in parallel in blocks of about 6. And if you were to rearrange these based on the time, then you'd see the blocks of 6 as they build up. Total download time, about 2.46 seconds. Now, if we look at exactly the same resource grabbed over HTTP, and I shift reload that, in this case, we are pushing the content, and I'll load that again just to prime the caches and so on. So we're pushing the content. You can see there is a single TCP connection. There are waits from the client, they get pushed out, and we're looking at a load time of around about 1.5 seconds. This example is largely bandwidth constrained rather than, so you won't see a phenomenal improvement using server push, but you see a small improvement because of the use of a single TCP connection and the preemptive push of resources. Now let's move on and take a look at gRPC. And I promised in this example, we would see an example of a client application that issues multiple different gRPC requests, and we'd use NGINX to terminate those requests and then load balance them across groups of servers. First of all, let's take a look at the client code itself. This is based on the Hello World example that's part of the gRPC toolkit. It's a small modification where we create a single gRPC connection here to the upstream server. In this case, it will be NGINX. And we issue repeated requests. So 10 times we say hello and we say goodbye down the same TCP connection, the same gRPC connection. These are 2 different gRPC methods as implemented in the protobuf specification. Here in the greeter service, it provides a say hello method, and in the dispatcher service, it provides a say goodbye method. We have a pair of very simple servers, one server that satisfies the say hello method and one server that satisfies the say goodbye method. So here we say hello, we say goodbye repeatedly 10 times down the same connection. We can look at the NGINX configuration. Very straightforward. The magic starts here at line 18. We listen on port 1080, HTTP2 requests. We write to the access log. If we see a request for the greeter method, we send it to the greeter upstreams. We see a request for the dispatcher, we send that to the dispatcher upstreams. The greeter upstreams listen on port 40,000 and 40,001. dispatchers, 50,000 and 50,001. At the bottom right is our access log. On the bottom left, we're running our port servers. And here at the top left, we'll run the greeter client. This issues, so it just compiles, then it runs, it issues 10 requests in pairs of hello and goodbye. And the useful information comes from looking at the ports. We can see that the hello greeting goes to port 4,000 and 40,000 and 40,001. That's the greeter upstreams. The goodbyes go to 50,000 and 50,001. And because NGINX is implementing round-robin load balancing, we iterate between 40,000, 40,001, and then back again. At the same time, down the same gRPC connection, we're issuing the goodbye requests, and those are iterating between 50,000 and 50,001. A great way of tracking and debugging what's going on is to use the access log. And you can see here how the services and methods are used, the module name, the service name, and the method are used to construct the URL that's used by the gRPC method. It's a post request, so the parameters of the request are encoded as a protobuf and posted, and the response is encoded in the body, and the status code then follows as part of the trailer. So, in summary, NGINX 1.13.9 supports HTTP2 server push with two directives, H2 push to explicitly push resources and push preload on to allow or enable NGINX to inspect the response from the upstream, intercept the link header, and initiate pushes to the client. The 1.13.10 release supports gRPC proxying, very simply configured using a new gRPC pass directive that proxies connections using HTTP2. You can use prefixes gRPC : which is optional, gRPCs : to tell NGINX to use SSL when it proxies traffic on to gRPC servers, and location blocks and upstream groups can be used in the usual way to match requests and to define groups of servers that we wish to load balance to. As we wrap today's webinar, I'd like to remind you that each year we hold our user conference. This year in October, we'll be holding NGINX Conf 2018 in Atlanta, Georgia. It's a fantastic opportunity to learn about the NGINX roadmap, to learn what's happening in NGINX world, to meet many of our users, to understand the trends and the techniques that they're following. We have great speakers coming from our community of users talking about the ways that they are leveraging NGINX to deliver sophisticated, complex applications at scale and at speed. Early bird registration is open. If you're using server push, if you're using gRPC, we'd love to hear from you. Where we can, we love to publish stories, success stories, or articles in our blog as testimonials to how people are using NGINX. It's a great way for our users to raise their profile, and it's a great way for us to share with our broad open source community some of the potential things that can be done with NGINX. If you have any feedback, if you'd like to talk to us, please reach out nginx-inquiries@nginx.com. And so I'll draw the webinar to a close now, and I'm very happy to take any questions that have come in through the chat.
Thank you, Owen. As a reminder, please submit your questions via the question box on the GoToWebinar control panel.
Okay, so a couple of questions have come in, and please do send more. So one user is asking, are these features only available in NGINX Plus? And the answer, of course, is no. They're available in NGINX open source right now. About 75 to 80% of our development resources go directly into NGINX open source and make their way out to the community. And in particular, anything that has to do with standards compliance, supporting protocols, with performance, with stability, with the core functionality of NGINX open source as a web server and reverse proxy, any of those capabilities go directly into NGINX open source. Those features are then tested in the field, and in the following NGINX Plus release, they will be rolled up into that release. So currently, if you want to use server push, if you want to use gRPC support, that's absolutely available in NGINX open source. For our users of NGINX Plus, we'll be making an NGINX Plus release in the near future, and that will include those features, along with any improvements, performance improvements, or bug fixes that we have developed in the intervening time. So a couple more questions coming in. Do we support gRPC streaming as well as the simple gRPC request response protocols? And the answer is absolutely yes. These work in a similar fashion, conceptually, to WebSockets. There is an initial gRPC request to set up the stream, and then the data is shuttled back and fro between client and server. NGINX can proxy gRPC streams just as it proxies standard gRPC request responses. If you look in the log, if you look at the way NGINX processes requests, NGINX will intercept the initial HTTP request, the post request. You can use that to make a routing and load balancing decision, and then the stream is established, and it will remain for as long as the client and server keep that stream open. Is there a GitHub repo for gRPC and NGINX? Yes, there is. Our primary location for NGINX source is a system called Mercurial. Go to hg.nginx.org and you'll see the core NGINX source there. We mirror that source onto GitHub, github.com/nginx, so you can pull the content from there. We don't accept PRs, pull requests on GitHub. If you want to make a PR, then use Mercurial and submit that PR through the NGINX Devel mailing list. So if you just want to pull NGINX and build it, you can get it either from Mercurial, HG clone, HG pull, or you can get it from GitHub with a git clone and go from there. Do we plan to extend the gRPC functionality to support HTTP2 to the upstreams? So I mentioned previously that NGINX does not support plain HTTP2 to upstream servers. We support HTTP version 1 in plain text and wrapped in SSL. gRPC does use HTTP2, but it uses it in a very specific fashion. And the implementation we have developed is tailored to that specific use of HTTP2. We don't have plans at present to extend that further to support general HTTP2 traffic. That would mean a number of additions that would allow us to do all of the things we currently do with regular HTTP traffic, such as blocking, such as buffering content, such as streaming to disk, performing caching and the like. And we don't have plans to do that at present. This is because typically NGINX is deployed in the same data center, often on the same network segment as the upstream servers that it's proxying or load balancing to. HTTP2 brings benefits if you're running over a high latency network, but the overhead, the additional overhead of HTTP2 overrides those benefits if you're running over a fast local latency network. And so it's our belief that it's generally much more efficient to use HTTP or, if necessary, HTTPS for internal traffic between NGINX and very, very close origin servers. Okay, and that's all the questions that we've received so far. So I'd like to say thank you again for your time. I hope this has been useful. I'd encourage you, if you do use server push or gRPC in production, then please do let us know, either through the NGINX inquiries list, or you look at the blog posts, post some comments at the end, and we'd love to hear from you. So thank you again, and I look forward to talking with you at the next NGINX webinar.
Thank you, Owen, and thank you all for attending today's webinar and for your questions. If you wish to find out more about our upcoming webinars, you can follow us on our social media platforms, and you can subscribe to our newsletter on nginx.com. We hope you found the webinar beneficial, and we look forward to having you on board again soon.